SwayamPrabha. Digital India. Educated India.
Hello all. In this video we will be focusing on the design considerations and the practices used in the industry to design plastic products. So, this is in continuation to what we have been discussing in the previous videos about how to characterize the polymers, but now let us see how we can use these plastics to design and what are the design principles or considerations we need before we choose a specific polymer for a particular application at hand. So, we will start with selection of polymers, where we will look at few criteria one should apply before we can select a particular polymer which is suitable for a specific application at hand. After that, we will be looking into some of the design examples just to give a flavor about what design considerations one has to take care of, so as to take to use polymers in a specific engineering application. So, we will look that using three examples using a fan blade, a plastic pipe and a plastic gate. So, let us start with the selection of polymers. There are many criteria one should apply before we can narrow down into one specific polymer which is suitable for a particular application. So, one of those criteria is to look at the strength values. So, depending on the application, once you have done the stress analysis, you know what are the stresses coming in a particular application. And if you have chosen the polymer you are working with, then you can narrow down onto the stress values or the strain values a certain polymer component is stressed through. Then the next step is to see whether this particular polymer meets the strength values or does it operate without any failure during the operations. So, what are the values we are looking at? We are looking at a series of values starting with ultimate strength. So, let us say the kind of failure which is more important is the complete failure, then we look at ultimate strength. But there are some applications where even the change of the shape is critical. Then even before we look at the ultimate strength, we also look at the yield strength, so as to make sure the component does not deform plastically. And let us say now the kind of loading is not just quasi static, but also cyclic loads. So, then we need to look into the fatigue aspects, and an important material parameter for the fatigue loads is the endurance limit. So, some of these values are readily available either through the manufacturer or the design books. So, one has to refer to those data to look at these values and see whether the particular material we have chosen meets these criteria. And there are many other things like the creep rupture. Let us say we are looking into long periods of time, then we know because these plastics are viscoelastic materials, they creep. But we are looking at whether if we leave it for a long time, when does it rupture? Or instead of looking at the strength values, we could also look at the strains in terms of the ultimate creep strain, or the creep strain, which limit the use of these polymers. So, we have been focused on the strength values, meaning the values which are the threshold before failure of a material. The way we define the failure will all depend on the application at hand, whether we are having quasi-static loads or the cyclic loads, or are we looking at long times versus short times. Then the other selection criteria will be based on stiffness. So, it is not always failure is what we are interested, we are also interested in stiffness, meaning how much the change in shape is there. So, if you apply a load, maybe there is a change in shape. Sometimes the design is a good or bad based on whether it changes shape too large or too less. So, within these stiffness values, we can look at the instantaneous elastic modulus if we are only focused on the response instantaneously or at very short periods of time. But let us say we are looking for larger periods of time, then we also need to look into the creep compliance or the equivalent modulus of the composite. But let us say we have an cyclic loading, based on what we have discussed in the previous videos, we need to be more interested in the complex modulus, because that shows with time and temperature how the modulus changes. So, in this slide we have only focused on the strength values and the stiffness values, but these are not the only criteria we apply while designing any engineering material, and specifically while designing using polymeric materials. So, we are also looking at the performance parameters. So, let us say you have multiple materials which are feasible for this particular application at hand. Let us say you have 3 to 5 materials and you need to decide which of these is good. For the moment, let us assume that the strength and the stiffness, they are all meeting the design requirements. But then in addition to the strength and design, we also look at other parameters like cost, the weight of the component and all. So, how do we look at it? We are looking at the relative size, volume, weight or cost for equal strength. So, let us say we want a target strength to be met for this particular application, then we see, given these 3 or 5 options of polymers, which of these will give us with the least cost or the least weight or the least volume or the optimum size. So, equally in addition to the strength, we can also have equal stiffness, saying that let us say we are designing a slender member like a beam, and then we know that the deflection at the free end, let us say, cannot exceed by a particular amount. Then that is our design criteria, and we are looking at options or the material which meets that criteria. So, for the equal stiffness, meaning the deflection at a particular part of the member, we are seeing how can we maintain that within the limits by minimum cost, weight, volume or size. So, now we are evaluating the performance parameters, so as our design objectives are met or we are trying to minimize the resources. And lastly, there is one more criteria to be thought about, such as the availability of the polymers, because theoretically one might say, okay, for so and so application, so and so polymer is very good, but it is not always true that though technically a particular polymer is good, it all depends on the availability of the polymers. Can we afford a particular material or not, or can we machine that to a particular application at hand or not. So, starting with the ability to fabricate. So, we know that unlike metals, fabricating polymers is a bit tricky, because not all polymers is something where we can machine. Some of them need to be fabricated in one component, but it is not always possible depending on the features we are looking in the design. And then we have other issues like heat distortion, because as we know, polymers, the CTE or the expansions are large compared to metals, meaning the shape or the size of the component changes with changes in the temperature. So, we need to see what is the distortion of this component because of changes in the temperature and see whether they are within the permissible limits. And the other important thing is about the compatibility with environment. So, depending on a chemical environment, maybe it is humid environment. So, we need to see for these specific operating environments which has a specific chemical or a humidity, whether the polymer we have chosen is acceptable or not, which means will it survive these operating conditions for the desired durations we are intended to use this component. And the other things like toxic or health effects, meaning there are some component polymers which release some gases, which might be harmful depending on where we are using them. And of course, this glass transition temperature, as we have discussed in length in this course, is a very important criteria, because that helps to give a sense of how the polymer behaves with changes in the temperature. So, for example, we have already seen this multiple times, saying that if your operating temperatures are well below the glass transition temperature, the material is hard and it is in a glassy state. But let us say our operating temperatures are coming close to the glass transition, that is when the material becomes softened. So, maybe if we are looking at a stiff and a hard material, maybe we want to avoid these temperatures, because then we lose the structural integrity of that component. So, glass transition temperature helps us to make the decisions in a more rational way. So, in the last this slide and the previous slide, we have seen various criteria one should think about before we finalize a particular polymer for a particular application, or before we choose it for the design. But of course, these are not complete, in the sense like there might be other conditions, like let us say there is an impact event. So, how do we say a particular polymer is good or bad? It all depends on how much energy it can take. So, like that, what I am trying to say is these are only few of the important parameters to keep in mind, but it all depends on the application and the nature of the load, where we have to come back with a new selection criteria for these polymers. Having discussed this, now let us move into the design aspects with these polymers. We will start with design of a plastic fan blade. As you can see in this image, what we have is a blade. There are several blades attached to the central rotor. So, usually when we design these with plastics, there is some additional criteria one has to look into, unlike the same thing when it is designed with a metal. Okay. So, let us say in this design, we are more interested to see the clearance between this fan and a casing. Let us say we have a casing surrounding this, and we want to make sure that there is enough clearance such that when the fan is rotating, it does not come and hit the casing. So, we are interested in the clearance between the fan and the casing. So, let us say that is the design we are looking at, or that is the target we are to achieve. Then what is the rational way to look or to approach that problem? So, here it does not matter whether it is a metal or a plastic. The first thing to look at is what is the nature of the load. As we all know, we have centrifugal loads. So, because the fan is rotating, and because of this nature of rotation, it has a centrifugal force pointing outwards from the center of this fan. So, this is same for either it is a plastic or a metal. The only difference is this force will depend both on the speed of rotation as well as the density of the material. So, once you know these properties or the criteria, then we can estimate what are these centrifugal loads. How do we use these centrifugal loads? We use this to find what is the elongation in the fan, because now that we know the load, we can find the deformations in the fan, and this is a very standard way of finding deflections or the deformations. This can be found using any classical approach or any standard textbook. But now let us see, since we are working with plastics or polymers, what are the additional criteria to be taken care of. So, here the viscoelasticity plays a role, because now let us assume that these fans are rotating at a constant speed, which means there is this centrifugal force. But if we wait for long times, since there is a force acting continuously, there is a continuous stretch, right. This needs to be accounted. So, what we are looking at is the creep strain. So, if you remember, creep strain is if you apply a load, the deformation changes with time. So, how do we find those creep strains is a question. So, of course, by what we have discussed in the previous videos, one can apply the viscoelastic analysis and try to come up with the relations or equations to estimate this creep strain. But usually in the industry, there is an alternative approach of how to design in these scenarios. There, we use these isochronous stress strain curves. Now, let us see what I mean by isochronous stress strain curves. So, let us say we have these stress versus strain plots, and now we will look at constant times. So, let us say this is how usually these curves look like. Let us say these are the curves which are for a standard time, let us say time t1, t2, t3. What it means is, once you do a creep test or something like that, if you wait at time t1 and see what is the response, accordingly you will have a corresponding stress and strain. But as you change the time, we have a different curve. Let us say we are starting with 1 hour, then maybe if you wait for 10 hours, the stress strain response will be different. That is what we are indicating with this curve where done it at time t2. And similarly, if I further increase the time to, let us say here I was saying, let us say 0.1 for 0.1 hours, and let us say this is 1 hours and these are 10 hours. So, with changes in time, these are the isochronous stress strain curves we have plotted. Okay. So, basically coming back to this design of the fan blade, we need to see what is the operating times. Maybe it is in the order of 10 power 3 or 10 power 4 hours is the operating time of this fan. So, we need to ensure that if it is operating for so long, what are the corresponding strains. So, coming back to the centrifugal loads, let us say we found the loads F and we found what are the corresponding stresses. Then let us say this is the corresponding stress. Now, depending on how long we are conducting this test, we know what is the corresponding creep strain, right. So, once we know the stress, looking at the operating times. So, if it is 0.1 hours or 6 minutes, we have it, this is the corresponding time, corresponding strain, creep strain. But let us say if we are operating for an hour, the corresponding strain is somewhere here, let us call it epsilon 2, epsilon 1. But let us say we are looking for very long periods, this is when we have the creep strain is also very large. So, these are readily available plots available either from the manufacturers, or one can undergo these tests and develop these charts. So, once we have these charts, one can use these charts to readily come up with these creep strain values. And mind you, probably I have not mentioned, these are usually done at constant temperature. So, let us say this is done at 60 degrees centigrade for example. But let us say in a particular application, this fan blade is exposed to room temperature as well as a higher temperature of 60, then basically you need to look at both the charts, one with a temperature of 60 and then another chart with a temperature of room temperature, just to give you an idea or a sense of what is the creep strain. But in addition to this, usually we are also sometimes interested in the failure. So, for example, in this case, what are the kind of stresses we see? Do we see the tensile stress or a compressive stress? We do see a tensile stress. So, what is the expected failure mechanism? At least one of them is crazing. So, in most of these isochronous strain curves, they also show you a crazing curve. So, it is something like this. So, essentially let me write it down. So, if we are looking at towards the right of the curve, which means crazing has initiated and failure has started, but it is safe to be on the left side of the curve. So, for example, if you are looking again at a particular stress, it tells you at what time we are expecting to see this crazing or the corresponding strain where we expect to see crazing to occur. So, these are some of the things one need to take care of if you are designing these fan blade using a plastic. So, next let us move into the second design example, which is for design of a plastic pipe. So, I think most of us have seen these plastic pipes at home, but they are also used in an industrial scale, such as to transport fluids, might be water or oil or other stuff. And usually these are also pipes are sometimes underground, so which means they need to bear the loads coming from the surrounding. And as you can see in this top right figure, they are also outside. So, now let us see what are the materials which are a good candidate for plastic pipes. So, usually they are made up of PVC, polyvinyl chloride, or HDPE, which is the high density polyethylene. These are the common materials they use for these plastic pipes. So, one of the primary criteria one has to look at while designing these pipes is the swelling and the thermal expansion. So, let us start with the thermal expansion. As we have already seen in previous videos, polymers the CTE values are very high compared to metals and all. So, what it means is, let us say there is a change in temperature of 10 or 20 degrees, then they expand or contract by a large amount. Why is this important? Because let us say if you are looking at this figure and let us say this is the pipe we are focusing on. Let us say if the length of the pipe increases, then what happens? Then it should take a new shape, something like this, right. Once it takes a new shape like that, then there are some stress concentrations which can build up. So, let us say maybe around these joints, and then the stresses are much higher than in normal conditions. So, one has to take care of these thermal expansion because they do affect the stress state in these pipes. And the other thing is the swelling. Swelling meaning let us say most of these pipes have internal pressure because we have fluids flowing through, and because of the internal pressure, what is the kind of stresses they develop? They do develop these hoop stresses along the circumference of these pipes. But now once we have these hoop stresses for a long periods of time, what do we expect? So, we expect to see some creep strain. Therefore, it is important when we design these pipes to consider the creep modulus. So, depending on the kind of loads, as we all know, the creep modulus changes with time. Initially, it might start with a high creep modulus, but over the time the modulus values decrease. So, depending on the loading, like whether it is you are looking for short periods of time, then you look at short term creep modulus, but if you are looking for a long periods of time, of course then we look at the long term or the equilibrium creep modulus. But depending on again whether these are seismic loads or whether these are occasional loads, it all depends. Depending on that, there are standards which prescribe what is the creep modulus one has to look at. But again one can use those isochronous stress strain curves to help us with the initial design, to get a sense of what is the corresponding creep strain involved, such as to see whether these are in the permissible limits or not. Okay. Now that we have looked about plastic pipes, now let us move into the last example where we look at plastic gears. We might have seen these plastic gears mostly, let us say, in a printer or somewhere, but plastic gears are used also in structural applications to take loads. But when we are using plastic gears, there are several factors we need to take care before we finalize this design. So, first I will start with some advantages of using these plastic gears. We will also look at the limitations or disadvantages of using these plastic gears, and we will also touch upon what are the design parameters to be looked into. So, two of the advantages are cost effectiveness. Because we can use injection molding process, this makes it ideal for mass production as well as reducing the cost of manufacturing. And of course, this injection molding, one of the advantages, it eliminates your machining operations. As we have already seen previously, machining is something polymers are, not all polymers are good at. Maybe few polymers like Delrin are okay with machining, but not all of them are. Fewer other advantages include this low density. So, since polymers are much lighter compared to metals, they have lightweight, and because they are lightweight, especially if there is some rotation or moving components involved, the inertias, the corresponding inertias are less, and which is good because then the forces are less and the stresses are also small. And they have a good capability to absorb shock and vibration. This is because polymers are much more compliant than metals, meaning they can take large deformations before any permanent damage or failure occurs. Tolerances in plastic gears are less critical because of the greater compliances, which means we need not worry about the tolerances much, because even if there is a mismatch, the stresses build up because of that is very small, unlike in metals where the stresses build up is high and which can lead to failure. We are also looking at the availability to operate with no or minimum lubrication. Because the coefficient of friction with polymers is much less, they have better tribological properties compared to the metals. So, if we are applying it in low speed applications, maybe we can get away even without lubrication, but once we are looking at high speeds, high rotation speed, that is when lubrication is a must. So, we already mentioned that they have low coefficient of friction. There are few other advantages like corrosion resistance. Unlike metals, they do not corrode when exposed to humid environments, and they are very quiet in operation because they can, again, because of the greater resilience. Now that we have looked into various advantages of these plastic gears, now let us quickly look at what are the limitations. So, first of all, they are very less load carrying capacity. Unlike metals which can carry much higher loads, they are low load carrying capacity, mostly because the failure stresses are small for polymers. They are not designed to take very high loads, but moderate loads is something they are capable of. And secondly, we have already touched upon in previous slides, saying that they have lower accuracy because of these swelling or the thermal expansions. And again, coming to the same point, saying that they have greater dimensional instabilities, and again these instabilities are because of the thermal expansion and the moisture absorption. In both these scenarios, the size or the shape changes, and sometimes it is not desirable because it might introduce some new stresses into the gears. So, reduced ability to operate at extremely high or low temperatures. High temperatures we know because relatively the glass transition temperature is much lower for polymers compared to melting points of metals. Because of these relatively less temperatures, the operating temperatures for plastic gears are limited because you cannot go for very high temperatures. Similarly, we cannot go to low temperatures because then they become brittle and they fail easily. And lastly, the initial mold cost, the costs involved in developing these molds are very high, and that is one of the limitations for going with the plastic gears. So, we touched upon few of the advantages as well as the limitations by going with the plastic gears, but now let us see from a design perspective what are the points we need to look at. So, one of the major criteria we need to look at is how to handle these heat and moisture effects. So, first let us look at what is called as backlash and how does it get affected. Backlash is the clearance. Let us say here we have a contact, tooth to tooth contact, but to the left there is some clearance. This clearance is usually called as the backlash, which is very high in kinds of plastic gears, mostly to allow for the high coefficient of thermal expansion and the swelling because of the absorbed moisture. So, which means if we are a designer, we need to leave these bigger backlash to consider these CT and swelling effects. Secondly, lubrication. We already mentioned that the coefficient of friction is small for polymers, which means there are applications where we can go even without lubrication, but if we are looking at higher rotational speeds, then the temperature builds up because of this rubbing action when the gear teeth are engaging. But how do we control this temperature? One way is to lubricate this surface, because that lubrication will take away the heat and then the operating temperatures are maintained even within the gears. And lastly, plastic gears are also used in conjunction with metals, meaning you can have one of the gears as a polymer which is meshed with a metallic gear. There are few advantages of going with this option, mostly because when there is heat generation, plastic we all know is a poor conductor of thermal conductivity, but metal is a good thermal conductor, which means it can conduct or dissipate the heat. It acts as a heat sink, which means it can take away the heat coming or generated during these contact areas and therefore control the temperature of the gear. So, these are some of the aspects when someone is looking at the design or analysis of these plastic gears. So, now let us summarize what we have discussed in this video. So, we started with selection of polymers, meaning we looked at various criteria we have to go through before we select a specific polymer for a particular application. So, we looked at different strength values and the stiffness values one need to consider. We also looked at the performance, saying that for a equal strength or a equal stiffness, which of these polymers will give an optimized cost, weight or other parameters. And we also looked at the availability, meaning what is the ability to machine these polymers or the availability of these polymers in the cost of preparations. So, we also looked into three different design examples, starting with a fan blade, where we said we first need to look at the centrifugal forces that will help us to find the creep strain. How do we find the creep strain? We said either we can do the viscoelastic analysis, or especially in industry, people rely on these isochronous stress strain curves. So, we said later we moved on to these plastic pipes which are made up of either PVC or HDPE, saying that again we need to consider the hoop stresses as well as look into what is the swelling occurring in these pipes because of either water absorption or the constant stresses applied. There again we said isochronous stress strain curves can be used in terms of pipe design. Lastly, when we touched upon this plastic gear, we have seen there are several advantages of using these gears, but there are a few disadvantages one needs to keep in mind. And finally, when we are looking at the design, especially how do we take care of temperature and humidity effects, we said there are several aspects to look into, but lastly we also mentioned that there are some options where there can be no lubrication if they are at low speeds because of the less coefficient of thermal expansion. But if you are looking at high speed operations, that is when lubrication is a must. But sometimes it is also good to replace one of the gears with a metal because it acts as a heat sink. So, this should summarize what we need to know about few selection criteria for the gears and few design principles when we are trying to use polymers in engineering design. So, this with this we conclude this video. In fact, this is also the last video in this first part of the course, which is on polymers. So, just to give a quick recap before we move on to the next topic of composites, we started in the week 1 looking at the microstructure of these polymers and try to connect that microstructure with the mechanical properties. Later we looked into the unique mechanical behavior of polymers, and then we moved into the various mechanical models one can use to represent the behavior of polymers. We also looked into the stress analysis of polymers, specifically in the analysis of bars and beams. And in the final week, the week 5, we looked into how to characterize these polymers using instruments called as DMA, dynamic mechanical analysis. And in this video, we also showed a few selection criteria as well as design principles. With this, we are concluding the polymers part of the course, and in the next video, we will start discussing about composites. Thank you.